本日はスタンフォード大学、博士2年生の安永君をお招きして、知識を使って QA をするという最近の研究を発表してもらいます。トークは英語ですけど、質問はどんどん日本語でドリーとかにポストしていただければと思います。では、安永君よろしくお願いします。
はい、ありがとうございます。紹介ありがとうございます。今日はゆるくお話できたらなと思います。よろしくお願いします。ですね、今回お話しするのは、ラングエージモデルとナレッジグラフを使った、クエスチョンアンサリング。で、今年のナクルでも発表させていただく論文です。ラボメイトのポンユとアントワン、そして、指導教授のパーシーとユーレとの、共同研究です。
Question answering is a fundamental problem in natural language processing. And to do well, systems need to access relevant knowledge and reason of it. Typically, knowledge can be encoded in large language models pre-trained on unstructured text, such as BERT, or represented in structured knowledge graphs, such as Freebase and ConceptNet, where entities are represented as nodes and relations between them as edges.
今回のワークではこのような、マルチプルチョイスの、QA タスクを、ラングエージモデルとナレッジグラフの両方にある知識を使って解こうという内容です。
Both knowledge sources have complementary strengths. Pre-trained language models have shown great success in many QA tasks, thanks to its broad coverage of knowledge. But at the same time, they may not work well for interpretable or logical reasoning, such as hand-ring negation. On the other hand, KGs are more explicitly represented and suited to structured and interpretable reasoning. But knowledge graphs may lack coverage and be noisy. So in this work, our goal is to leverage both sources of knowledge and do better in question answering.
ラングエージモデルと KG には両方、短所と長所があって、両方のいい部分を組み合わせるっていうのが目標っていう感じですね。
So why is this problem hard and interesting? Let's say the system is given a common sense question, asking, if it is not useful here, a round brush is an example of what? Along with some answer choices like hairbrush and art supplies. We call the set of question and answer choices like this a QA context. Given a QA context, and possibly encoding it with language models, the model needs to first identify informative knowledge portion from the large KG, such as the green box here, and then the model needs to capture the meaning of the question, including a negation in the question, as well as the structure of the knowledge graphs, like the relation between entities, to perform joint reasoning. So these 2 points listed here are interesting research challenges in this problem.
この問題特にあたっての課題は、このクエスチョンが与えられたときに、まず関連のある適切なナレッジグラフの一部を見つけてくるという必要があるということと、その後テキストの部分とナレッジグラフの両方を使って、推論をするという、その2点が、面白い課題だなということです。
In this work, we present QAGNN, a new hybrid model of language model and knowledge graph to solve those challenges. Let me first give an overview of QAGNN. First of all, given a QA context, we will use a language model to encode it into a vector representations, and then use a standard method to retrieve a knowledge graph subset, like linking entities and getting their neighbors on the knowledge graph. Then, QAGNN is based on 2 core ideas. First, in order to better identify which knowledge graph nodes are relevant to the current question, we propose language condition KG node scoring, where we use a pre-trained language model to compute the probability of each KG entity conditioned on the current question. And secondly, to jointly reason with language models and knowledge graphs, we connect the question text and KG to form a joint graph, which we call working graph, and then mutually update their representations via graph neural networks, GNNs. Finally, we combine the representations of the language model and KG to predict the final answer.
こちらがその、提案手法の全体像で、先ほど述べたその2つの課題に対して、それぞれ解決案を述べていくという感じですね。で、この1番と2番の部分です。
In what follows, I will introduce these two ideas in more detail. Our motivation of proposing KG node scoring is to better identify relevant knowledge from KGs, given a question. Let's say we have this question asking, a revolving door is convenient for two-directional travel, but also serves as a security measure at what? And answer choices like bank. The real-world knowledge graphs are huge with a million entities, and existing methods to extract a KG subset is to identify entity in the QA context like travel, door, security, and bank, which we call topic entities, and then retrieve their one or two hop neighbors from the knowledge graph. However, this may introduce many entity nodes that are semantically irrelevant to the QA context, especially when the number of topic entities or hops increases. So in this example, one hop neighbors may include nodes like holiday, riverbank, human, and place, but they are off topic or too generic to be informative. To address this challenge, we propose to use a pre-trained language model to score the relevance of each KG node conditioned on the question. Specifically, we concatenate the QA context and each entity in the KG and feed it into the language model to compute the probability of each entity. Now, all the nodes in the KG are scored with respect to the question, like in the diagram, where the darker green indicates higher score. For example, entities like robbery and safe have higher relevance score now, and entities like riverbank may have lower scores.
既存のそのナレッジグラフのリトリーバルの方法では、クエスチョンと関係性が低いノードもたくさんリトリーブされてしまうので、このグレーの部分ですね、左の。このワークではラングエージモデルを使って各ノードの関連性をスコア付けして、さらに KG を絞り込むというアイディアを提案しています。
The next natural question is how to use this relevance score. One option is to use them to prune KG nodes so that the KG fed into a model can be smaller, which can help to improve the time and space efficiency. Another option is to use the score as an additional feature of KG nodes, which provides a general way to weight information on KG. And we will pursue this direction in our graph neural network architecture we will introduce next. So the next model component is joint reasoning. To design a joint reasoning space for the two sources of knowledge, we explicitly connect them in a common graph structure. We introduce a QA context node, Z, and connect it to each topic entity in the KG. As this joint graph intuitively provides a working memory for reasoning, we call it working graph.
そのクエスチョンとナレッジグラフの情報をもとに、同時に推論をするために2つのモダリティをジョイントさせたワーキンググラフというのを作るというアイディアです。
Each node in the working graph is associated with one of the four types. Purple is the QA context node, and blue is entity in question, orange is entity in answer choice, and gray is other entities. The initial node representations for the QA context node is the language model encoding, and node representations for other nodes are pre-trained entity embeddings. The working graph essentially unifies the two modalities, text and KG, into one graph. To perform reasoning on the working graph, we design a attention-based graph neural network message passing. The basic idea of GNN is to update the representation of each node by letting neighboring nodes to send message vectors to each other for multiple layers. Concretely, in our model, we update the representation of each node T by this rule here, where M is a message vector from neighbor nodes S. Alpha is the attention weight between the current node T and neighbor node S. The sum of these messages are then passed into an MLP function. The message vector M is a function of the node representation of the neighbor S, its node type embedding, and the relation embedding between T and S. For the attention weight computation, we want to incorporate the node relevance score we computed earlier. The basic way to get an attention weight is to prepare a query vector Q for the source node and key vector K for the target node. We let the key and query vectors to take the node relevance scores as an argument, and then use the query and key vectors to compute their attention weight using inner product.
簡単に説明すると、その先ほど作ったワーキンググラフにグラフニューラルネットを使って、representation、ノードの representation をアップデートして、QA タスクを学習させるというアイディアです。
Okay, so this is the recap of our overall approach, and we have covered the two core ideas proposed here. Now, I want to talk about the evaluation of our method. As an experimental setup, we use two popular QA benchmarks that requires reasoning with knowledge. One is Common Sense QA, which has multiple choice questions testing common sense knowledge. Another dataset is Open Book QA, which has multiple choice questions testing elementary science knowledge. For knowledge graphs, we use ConceptNet, which is an open domain KG with close to 1 million entities. Following prior works in the research field, we link entities in each question to the ConceptNet and extract a subgraph of 2-hop paths to be our input KG. Our KG node scoring idea is performed after this preprocessing. The main systems we compare with are fine-tuned language models like Robeta and previous language model plus KG models such as RelationNet, CAGNet, and MHGRN. The main difference between them and our proposed QAGNN is that we estimate the KG node relevance with respect to questions and weight KG information, and that our model mutually updates the language model and KG representations on the joint graph, while prior works combine language model and KG representations only at later stages.
今回のこの QAGNL の、新規性は、まずそのラングエッジモデルを使って、ナレッジグラフのスコア付けをするというのが1点。そして、このワーキンググラフっていうのを作ることによって、ラングエッジモデルとナレッジグラフのレプレゼンテーションを、相互にアップデートして推論学習させるという、2つがメインということです。
For fair comparison, we use the same pre-trained language model, Robeta, for all the systems shown here. Here are the experimental results. We find that QAGNN achieves an improved performance over previous systems on the two QA benchmarks. To see the effect of the two main ideas we proposed, we also conducted an application study. We find that if we do not form the joint graph of text and KG and mutually update representations, the performance drops about 2%, which is now close to the previous LM plus KG models. We also find that removing the KG relevance score hurts the performance by about 1%. We also find that the KG node scoring tends to help when the number of entities in the question is larger or the size of the retrieved KG is big. On the other hand, the joint graph representation and message passing tend to help when the question has negation.
発見としては、そのナレッジグラフのスコア付けは、リトリーブされたナレッジグラフが大きいときに、特に役立って、ワーキンググラフの方は、否定文とかの難しめな推論を必要とするクエスチョンの際に、特に有意義だということが分かりました。
Next, I want to share some case studies of the model. Here, we try to interpret the model reasoning. Given the QA context, we try to trace the attention flow computed by QAGNN from the QA context node, the purple node, to question entities and to other entities in the KG. In this example, we find that QA context node attends to elevator and basement, and they attend to building, and building attends to office building, which is the answer. This helps us to find a reasoning process from the model. In the second example, we try to trace the attention flow from the QA context node to both question entities and answer entities. In this case, crab on the left and salt water on the right. We were able to find bridging entities on the KG, such as sea and ocean. We also find that QAGNN can handle some robust reasoning, such as 100 negation and entity substitutions. For example, consider this question: if it is not used for hair, a round brush is an example of what? Because the question has a negation, the correct answer is our supply rather than hairbrush. In this original negated question, the model attends to the correct answer, round brush. We then flip this negation in the question on the right. Now the model attends to the entity hair and predicts hairbrush correctly. In the second example, we change the entity in the original question, changing hair to art, and we find that the model adapts the answer accordingly to hairbrush. Here I'm showing more examples of testing such robust reasoning, like changing negation and entity names. And we find that language models like Roberta fails in those tests, but QAGNN seems to handle some of them correctly. Finally, I want to summarize the takeaways of this talk. Our motivation was to combine two sources of knowledge, pre-trained language models and knowledge graphs, and do better in question answering. To solve this problem, we introduced a new model, QAGNN, which has two innovations. We use language models to score the node relevance condition on the question. This is a general framework to weight information on KG, like soft retrieval or pruning. We then propose joint reasoning with language models and knowledge graphs, where we connect the text and KG to form a joint graph and mutually update their representations. QAGNN achieved promising results on QA benchmarks, with some takeaway insights that node scoring tends to help when the retrieved KG is big or noisy, and that joint language model KG message passing tends to help when the question requires rich reasoning, such as negation. Thanks for your attention, and I'm happy to take any questions.
以上です。ご清聴ありがとうございます。コードとかも、データとかも公開してGitHub で公開していますので、もし興味がありましたら、ぜひ見てみてください。